Now coming to the last topic of this chapter, which is on dimensional analysis. Let us first ask the question, what are the dimensions? In physics, dimension refers to the physical nature of a quantity and is expressed in terms of basic measurable units, which we call a fundamental or a base quantities. For example, length has the dimension of L. Time has the dimension of T, and mass has the dimension of m. When we combine these base quantities to describe other physical quantities, we define their dimensions. For example, velocity is distance divided by time. So, its dimension will be L t minus 1. L for the distance, and because it is divided by time, so t to the power of minus 1. Similarly, the force is defined as the mass time acceleration, and the dimension for mass is m, while for acceleration it is L t minus 2. So, the dimension of force will be m L t minus 2. Coming to dimensional formula and equation. A dimensional formula expresses the quantity in terms of the powers of the base units. For example, volume can be written as m to the power of 0, L to the power of 3 and t to the power of 0. Similarly, the speed, which we discussed earlier, can also be represented as m to the power of 0, L to the power of 1 and t to the power of minus 1. And force can be represented as ml t to the power of minus 2. A dimensional equation simply sets this formula equal to the symbol of the quantity. For example, the dimensional equation for volume, speed and force may be expressed as V m0 L3 T0. Then velocity small v has the dimensions of m to the power of 0, L to power 1 and t to power of minus 1, and force has m L t minus 2. So, these are called dimensional equations. There is a principle called principle of homogeneity. According to this principle, every term in a physical equation must have the same dimension. For example, if one term has a dimension of L, all other should also have the same dimension. Let us look into the example. Here is an equation which is x equal to x naught plus v naught t plus half a t square. Now, let us check each term. x0 is the distance, has a dimension of L. v0 t terms. v0 is the velocity, so it has a dimension of L t minus 1, and small t here represents the time, so which has a dimension of t. So, when you combine all these dimensions, the dimension of v0 t also comes out to be L. Now, looking into the third term, half a t square. A is the acceleration, so it has a dimension of L t minus 2, and t square has a dimension of t square. So, if you combine all these things together, you come up with length L. So, we see all terms here have same dimension L. So, this equation is dimensionally consistent. If suppose there was it was not true, some terms were not having the same dimension, then you can say that equation is dimensionally incorrect. So, it is very good way to check the validity of the equation, whether some equation is correct or not. If it is dimensionally incorrect, then it means equation will be incorrect. So, let us verify a real equation, which is kinetic energy equal to potential energy. So equation for kinetic energy is half mv square, and for potential energy it is mgh. So let us see whether dimensions are consistent or not. On the left hand side, mass has a dimension of m and velocity has Lt minus 1. When you square it, it will become L square t to power minus 2. And when we put it together, the dimension of left hand side is m L2 t minus 2. Now let us look into the right hand side. Right hand side has mass and then acceleration due to gravity and height. Dimension for mass again is m. For acceleration due to gravity is L t minus 2, and height has a dimension of L. So if we combine all these things together, we again end up to m L2 t minus 2. So both sides simplify to m L2 t minus 2. This confirms that equation is dimensionally valid. In this way, you can check any equation and can verify whether that equation is correct. So now I will show you how you can use this dimensional analysis to derive some simple formulas. So let us take the example of pendulum and derive the time period of a pendulum using this dimensional analysis. For this, the first thing that we will assume is that time period t is given by a following expression, where k is a constant, L is the length, g is the gravitational acceleration, and m is the mass. So time period of a pendulum is k times L to the power of x, g to the power of y, and m to the power of g. Now let us look into the dimensions both on the left hand side and right hand side. Left hand side, the dimension is simply t. On the right hand side, we have to put the dimensions of all these individual quantities like length, g, and mass, and appropriate a power. So L to the power of x times L t to the power minus 2 whole to the power of y, and then m to the power of z. If we simplify, on the left hand side it remains t, while on the right hand side you see L to the power of x plus y, t to the power of minus 2y, and m to the power of z. Now match the dimensions on both the sides, because length on the right hand side is x plus y, on the right hand side is x plus y, on the left hand side you have 0. Similarly, when you compare the dimensions of t, you get minus 2y equal to 1, which gives y equal to minus half, and then m to the power of z, and there is no m on the left hand side, so z equal to 0. So if you simplify these simple equations, you get x to the power of x equal to half, y equal to minus half, and z equal to 0. So now let us put back all these numbers in this first equation, and we get t equal to k to times L to power half and g to power minus half, which can be written as k equal to t equal to k times under root L by g. And we know that for the pendulum, that period is given by the similar expression. What are the limitations of dimensional method? While useful, dimensional analysis has limits. For example, it cannot give dimensionless constants like 1 by 2 or 2 pi. For example, in the derivation of time for pendulum, we could not find the value of k, the constant, although we could find all other quantities, but that dimensionless constant cannot be figured out. It cannot distinguish between quantities with same dimensions and does not apply to non-algebraic functions like sine or log.